Good morning, good afternoon, and good evening, everyone, wherever you might be. So today we're going to be continuing our lesson on linear systems. So we stopped at, well, let's do a quick recall. So we basically talked about Gaussian elimination, which is a way of solving a linear system of equations. And then we decided to compute its time complexity, and we realized it's O of n cubed. And then we tried a decomposition or a technique that we can use to reduce the complexity or the time. And we did LU decomposition. So we broken down a matrix into its lower triangular and upper triangular matrix. And we've made a coupled system. So once we've broken down A into LU matrices, we assigned Y to be matrix U times vector X. And then we've also done Ly equals B, where L is a matrix, Y is a vector. And both of these have a computational complexity of O(n) squared, which is much, much faster than Gaussian elimination algorithm. And yeah, so basically the idea is if we were given an AX equals B linear system, it's usually or almost better to use LU decomposition as opposed to just using Gaussian elimination because it makes the whole thing faster. Okay, and then now we stop here at permutation matrix. And so as will often happen with Gaussian elimination, following the above algorithm will at times result in a zero pivot. This is easily handled in Gaussian elimination by shifting rows in order to find a non-zero pivot. However, in LU decomposition, we must keep track of its row shift since it will affect the right-hand side vector B. And so the purpose of the permutation matrix, one of the purposes here is we can keep track. So we can keep track of row shifts. With a row permutation matrix. So we're using a row permutation matrix in order to keep track of the row shifts. Let's call it P for permutation. So if we need to find two rows, then we basically do. So here's the system that we want, AX equals B. And we multiply permutations to both sides. And then we do an LU decomposition. Right? Okay. Actually, we just do LU X equals PB. And here we say PA is equal to LU, where PA no longer has zero pivots, right? So for instance, if we were to shift rows 1 and 2, so if we shift rows 1 and 2, we get, okay, my V is a little bit weird. We W. We got P 0 1 0 1 0 0 0 0 1. So here, right, I keep on shifting and I keep going here. And thus the permutation matrix starts with the identity matrix. And if we need to shift rows J and K, then we shift these corresponding rows in the permutation matrix P. And if permutation is necessary, well, Python can supply the permutation matrix associated with the LU decomposition. So I'm actually gonna try to dive more deep into this permutation matrix. Yeah, I want to see what this is really about. Maybe I can. So, okay, a permutation matrix is just an identity matrix with its rows rearranged. Each row swap in the original matrix A corresponds to a row swap in B. Okay. So basically, okay, yeah, we can keep track of the row shifts. Yeah, so just to explain permutation matrix a little bit more, um, we're saying that each row swap in A, we're saying A is a matrix here, corresponds to a row swap in B, right? So, uh, so let's say we have this identity matrix, right? Which is 3 by 3. Let's say we have this identity matrix. Three by 3. And, well, we want to swap rows 1 and 2. And so we use that in our permutation matrix B. Or we apply that in our permutation matrix P. So P is then now row 2 first, then row 1, which also has 3 by 3. Then we say PA is actually just equal to LU decomposition. So if we multiply this matrix with our A matrix, it's actually just our lower and upper. So LUX is equal to PB. Okay. Let me actually go through it in Python. Let me see. Should I go through it in Python? Okay, I'm gonna go through it in Python. Stop share. Oh, I can minimize. Oh, that's too bad. Okay, let me just. Okay, I'm gonna share. I hope this is visible. right? Let's see if it's visible. Can okay, it's showing. Actually, let me open. Ah, yeah, let me open VS Code here. Okay. File, new file, Python file. Um, I should have done this before. Anyways, uh, can I want to make a new file? Oh, there we go. Nice. Okay. I'm going to share another thing here. Can I share this? Oh, there we go. Okay. Okay, uh this is really visible. Let's see. What am I sharing? Okay, cool. So, uh, yeah, let's apply this in code. Because what's scientific computing without code, right? So the first thing we want to do is we want to import libraries, right? So here we're going to be importing uh, some libraries here. We'll import NumPy. I'm not going to explain what these are, but it's just a way for us to actually see what what's happening here. Okay. SciPy, linalg. Apparently, linalg means linear algebra. Okay. And so the first thing we want to do is create arrays for matrix. Let's create matrix A and vector B. So A is just NP. So these are just packages, and we can use them to create some stuff. Let's do 1, 1, 1. So this is a 3 by 3 matrix, right? Let's do 1, 2, 4. And then 1, 3, 9. I hope this is visible. If it isn't, then that's too bad. Okay, let me see if I can run it. Oh, okay. Uh, what do I name my file? Let's just name it um what do I name it? Let's name it scientific. Okay. Uh, is it run? Oh, cool. There we go. Oh wait, what happened? Array takes from one position. But three were given. Takes one from two. What does that mean? One, two. What? Supposed to be. Let me just double check what I did. Okay. And then I'm just testing because I haven't used VS Code in a while. There we go. Okay. So yes, we have this matrix, 1, 3 by 3, right? Can't see it. Oh crap. I lost it. Okay, I guess I can't zoom it in. But we can see this matrix. It's 3 by 3. And we're gonna create our vector as well. And it's gonna have the elements. It's a column vector. So 1, -1, 1 again. Okay, it ran. That's good. Can I clear these? I just killed the terminal. Okay, the next thing we want to do, so we can try doing a direct uh, Gaussian elimination here. So NP dot then I'll solve. Right. So here we're actually we're solving for x, and here we're just using so here we're solving for x. Okay, and then we're gonna so this is actually just using Gaussian elimination. Right? And then okay, we can print x. Let's see what it does. Should give me something here. And there. So we have some x values that we got. 7, -8, and 2. Okay. And let's also try solving it using an LU decomposition. So that's the Copilot's saying it. Then I'll just dot a LUA. And then from there, so that was Gaussian elimination. Yeah, so that one gives me PA equals LU, right? And then here's where our permutations come in. So you're going to say V2 equals uh, NP dot mat mule V. So here we're actually applying the permutation matrix P. So that's what we're doing here. And then we solve for y, right? Our Ly equals b. We solve for y, and we solve for x. So let's just do that. NP dot, and now we should solve b2, right? So here's that solving for Ly. Oh, a bit laggy. It's that solving for Ly equals BB. And then we do our x. So our x is now NP dot, then I'll dot solve UI. So this is where we solve that ux equals y. And then let me actually print both of them. And here we do. So let's see. And ideally, right, we should get the same thing which we did. See here, when we did a Gaussian elimination, we got these values for x. And when we did an LU decomposition, we got the same thing. Now you might be wondering, okay, well, how do we determine which one's faster of both algorithms? So let me actually just, okay, let's actually test the runtime. Let's try doing that. Okay, let me, okay. So here uh, we're gonna import another library for this. We're gonna import time. And I don't think I have this. Oh, I don't. Okay. Let me just install the, The library? Oh, oh, there's none. Okay. That's okay. Okay, that's funny. Oh, okay. Actually, we can't really do that because it's just a 3 by 3. So we should try um doing it with maybe a bigger matrix, just so that it'll actually make sense. So let's try. Okay, let's do this. So here I created a 500 by 500 matrix, and then we did a timer here. Let's see how long it took for both, or how long it will take for both. And look at that. Huh. Let's try again. Let's keep going. Okay. So far, direct solve time is way quicker than LU solve time, right? Surprise. That's a 500 matrix. So LU, I mean, direct solving is way, way quicker than LU. But when we computed it in theory, it shouldn't be. What if we make our matrix bigger? Let's try that. Okay, I'm just gonna, yeah, let's see. Because ideally, right, our LU should be quicker. At least so. Yeah, apparently LU is way fast, way slower than direct one. That's funny. If I do this. Okay, now I cannot if I do that. So now I'm just adjusting the size of my matrix. I'm trying to see. Um, okay, now it's taking a while because it's 10,000. Let's wait for it. I mean, I kind of don't want to wait for it, but whatever. Hmm. Oh, oh, okay. So Python's doing something to make it quicker. Oh, never mind. Yeah, Python's doing something to make it really quick. Oh, okay, okay. So direct solve time took 16 seconds. But yeah, uh, can I? Okay, I want to adjust the code to edit my direct solve timing. Let's see. Because Python is making it more faster. Python's optimizing it. Uh, yeah, we want to use that regular Gaussian elimination. Okay, let's okay. I'm just gonna copy paste this because I'm just making it as quick as I can. Yeah, because lineage makes it optimized. So let's try it without the or well, let's try it with this. So this one's manually solving it underneath the hood. Let's see how long it takes. So manually, yeah, manual direct solve time takes more than LU solve time. Yeah, that's one we, yeah, because the previous one, Python already optimized that. It already created an algorithm called the linear algebra. Yeah. So that's why it's quicker there. But yeah, here's the manual direct solve. So here's yeah. So they created a function here, Gaussian elimination, forward elimination, back substitution. And then my LU, which has lineage. Okay, cool. So that's the basic idea. Can minimize this. But yeah. Um for for computers, well, it's better to use LU decomposition instead of Gaussian elimination in this case. Or it's better to optimize it with Python, but haven't yeah. Anyways. Um okay, so that's that. Next thing we're gonna talk about is well, iterative methods, right? Because we talked about um what was this? Direct methods. And I guess there are other ways or techniques to solve for AX equals B. So we're going to use iterative methods this time. Now, am I sharing it? I'm not sharing my screen. I'm okay. Let me quickly share my screen. Okay, so iterative methods. So in addition to standard techniques of Gaussian elimination or LU decomposition for solving AX equals B, a wide range of iterative techniques is available, right? And these iterative techniques can often go under the name of um, what in the world? Krylov space methods. Let me just Google that real quick. Krylov space methods. What is that? Um, Iterative numerical methods. Okay, I'm not gonna go into that because it's linear algebra. I haven't taken a linear algebra class before. Um, we're just gonna go through the basic iterative solution methods here. So the idea, so here's the idea, right? So the idea is to start with an initial guess. That's what we want to do, right? And our initial guess is, let's say, x equals x naught. We can say that. And then we develop an iterative procedure that will converge to the solution. So that's the start. Start with an initial guess. And then we sort of develop something that repeats again and again. So some process of repeating again and again that will converge to solution. So it will get closer and closer until we reach that solution. Okay, let's start explaining that actually. So there's okay, so the simple example of this method, well, the simplest example, we're gonna use what we call a Jacobi. Actually, let's just write this. So we're gonna use what we call a Jacobi iteration scheme. Okay, so let's consider an example, right? is the simplest method. Okay, here I'm just like making notes for myself. Let's consider an example. So here we're being asked to consider a linear system. Okay, so this linear system has has three unknowns. 4x minus y plus z equals 7. 4x minus 8y plus z equals negative 21. Negative 2x plus y plus 5z is equal to 15. Okay, so that's our linear system. And basically the Jacobi iteration scheme is, again, we're going to start with some initial guess, right? So, okay, well, convergence of the Jacobi iteration scheme to the solution from initial guess. Okay, let me see. So let's say start with initial guess, right? Because that's the first step. So we're gonna say my initial guess, or my x naught, is going to be, we're gonna just combine it into an ordered triple. My x naught, y naught, z naught is equal to 1, 2, 2. Right? I'm just copying what the textbook is saying. And then as I continue, I should be able to get to a solution, right? So this is where k is equal to 0. And then I continue, right? So my k converge to solution. So that's what's happening here. So here my k, I'm going to make a little table. My k starts at 0, right? Then I have my xk. I have my yk, and I have my zk. So that's the idea, right? So we started at 1, 2, 2, and then we continue. So we go 1. Now here I'm just picking points, right? I'm not trying to give an exact solution here. I'm just picking points. So now this is 1.75. Again, I'm just picking points. 3.375, 3. And then 2, I don't know. For 2, I got, okay, here's just the textbook. 84375. Don't know where you got that number from. 3.875. But here I'm just introducing again. Here I'm just introducing this idea of what it means to start from an initial guess and eventually it converges, right? So I keep going. And then I get to, well, I get to, okay, so here I apparently get to some value. I got to 15. And I get 1.999993, 3.999985, 2.99993. So here I'm actually getting close. And by the 19th iteration, well, I actually go to a value, 2, 4. 3. And then that's the final, right? So here we can see that actually converges to a solution. So here I say converges to solution x, y, z, which is equal to 2, 4, 3 from my initial guess. And my initial guess was x naught, y naught, z naught, which has 1, 2, 2. So it's the idea of getting closer and closer to a value. Okay, now so this is the intuition. Now let's actually try doing this mathematically. So mathematically, we can rewrite the system, our linear system, as follows. So here we're saying x is now equal 7 plus y minus z equals 4, right? Because from here, we isolated x in terms of y and z. I'm going to do the same thing for the others. So y is now 21 plus 4x plus z all over 8. And my z is now 15 plus 2x minus y all over 5. And now to solve the system iteratively, so to solve system iteratively, my bad. We define the following Jacobi iteration scheme, right? So we define our Jacobi iteration scheme. So how do we do that? Well, from our previous one, right? So here I'm saying my x, k plus 1, I'm just going to write it out first, is 7 plus yk plus zk. Or no, not plus zk, minus zk. So here we can see that, oh, I plug in these values and I get the corresponding x after. Because it's k plus 1. I get the corresponding element after. Right? So I have my initial guess. I isolate them, right? I solve them in terms of x, y, and z. And then I keep going until it converges to a solution. And I actually don't have to do this manually. Why? Because there's code that does this for me. And I'm going to show that later. 21 plus 4xk. So here I'm just putting k's. Zk over 8. Then lastly, 15 plus 2xk plus, or no, not plus, minus yk over 5. So that's the idea. So we keep on going. There's a computer that will do this for us. We just have to code it, basically. But we keep going until we find the exact x, y, z. If we don't, then it's not convergent. So an algorithm is then easily implemented computationally, right? So we can actually just implement this whole thing using code. So basically, we give an initial guess, right? So that was random. So when we chose 1, 2, and 2 for our x naught, y naught, z naught, it's actually random values. And we just use this algorithm, right, in code, and then it will lead us to the solution. So we guess our initial guess. Sounds funny. So we guess our initial guess. That's the first step. And then we iterate the Jacobi scheme. So that's going to be, well, yeah, my x k plus 1. Okay, where did that come from? There's some new notation here that I don't. Okay. Where in the world did this come from? Okay, let me quickly check. There's a new notation that I found weird. But yeah, we can use code to solve for this. What's the notation? Oh, okay, so it's a matrix form. Okay, cool. So D is the diagonal matrix, L is the lower, use the upper. We rearrange, we multiply both sides. Okay, I'm not gonna use this. Actually, I mean, there's a proof as to how we got this notation. Okay, let me just go through the proof. So we iterate the Jacobi scheme, right? So we start off with AX equals B, right? That's our system, where A is a square matrix, X is an unknown vector, and B is the right-hand side vector. And here we actually split A into three components. We say A has this D plus this L plus this U, where D is the diagonal matrix of A, right? We know what LU is. L is the lower triangular part of A and U is the upper triangular part of A. And then we rearrange this. So we say that dx k plus 1 is basically negative L plus U x k plus B, right? Now, how in the world did that happen? Well, my A is dLu, D plus L plus U, right? I leave the D here. I don't know how I did that. Minus L plus U. And then I multiply both sides by its inverse. Okay, there's some matrix algebra stuff actually that I'm not super familiar. But basically, okay. So now we want to isolate. So we multiply it by its inverse. So D minus 1, then minus L plus U, X sub K plus B. Okay. Or equivalently, it's just this, the inverse, and then we say D minus my A matrix X K plus B. Yeah, so this was the notation I was trying to say, but I guess yeah. Yeah, but this is just the compact form of the Jacobi iteration method or scheme. Anyways, I'm not gonna dive deep into that. Maybe in a future course I might go back to it. And then lastly, we check if it converges, right? So we check if it lands to a solution as we keep going. So we check for convergence, and that is if my initial guess, so we call this the norm. So we're checking if it converges. If the norm of my following solution from my initial guess is less than what's being tolerated. So it's less than the error that we're looking for, right? So here we note that the choice of an initial guess is often critical. So I mean, you can't just guess and guess, right? It's actually important to guess the right guess. So it's important to guess that in determining the convergence of the solution. So thus, the more that is known about what the solution is supposed to look like, the higher the chance of successful implementation of the iterative scheme. Although there is no reason a priori to believe this iteration scheme would converge to the solution of the corresponding system, AX equals B, well, our previous table, right? Our previous table shows, this table. This shows that the scheme converges quickly to the solution for this simple example. So given the success of this example, it is easy to conjecture, so it's just a conjecture, that such a scheme will always be effective. But we're not entirely sure of that. So however, we need to reconsider the original system by interchanging the first and last set of equation. The first and last set. So let's actually try and do that. What if we switch, right? So from this linear system, what if we switch these two? How's that gonna look like? Uh, However, we can reconsider original system by interchanging the first and last set of equations. So we got this thing here. I don't know why. Ooh, I bet. Let me let me drag. That's funny. Okay. Why is it doing this? Okay, I switch to my pen, I switch back. What happens if I do that? Oh, okay. This is what Oh my goodness. What if I do a lasso here? Ah, much better. Okay. Oh my goodness. Wait, let's move. What? Okay, I give up. That's it. I'm just gonna write everything. Okay. Now even my pen's having issues. Sorry for the technical difficulties. Okay. I'm just gonna rewrite everything. So basically I'm switching my last and first equation. So let's actually see if this will affect it, right? Plus z equals -21, 4x minus y plus z is equal to 7. Okay, let's see. So if we actually do a table, well, okay, we do xk, yk, zk. Oh no, please don't. Okay, finally. So if we actually do a table here, and we start with an initial guess of 1, 2, and 2. And if we do a 1, well, now it's going to be different, right? Because we've changed our order. So when we changed our order, we'll have different values here. So let me just maybe give this one, and then I'll just say a few things about it. But it's actually going to go infinity. That's what's happening here. Meaning it diverges, doesn't converge to a value. So this is a divergence of the Jacobi iteration scheme. Yeah, so it diverges. From my initial guess of 1, 2, 2. Because I changed the order. So if we were to solve it iteratively, right, we would get a different um, we would get a different set of iteration here. So to solve system iteratively, we're just gonna write it out. So we do the same thing, right? Here we isolate x, y, and z. And we start from the top. So we got xk plus 1. Now it's different. So yk plus 5zk plus, not plus, minus 15. So if you notice, this is actually different from what we used to have because we used a different one for xk plus zk. Yeah, this would have been easier to visualize if I put it in code. I'm gonna put it in code. I'm just explaining all the nitty-gritty stuff first. Yk minus 4xk plus 7. So here we see that this iteration scheme is different from this one, right? It's different. And here it doesn't converge. So our iteration scheme fails. right? Yeah, since our k actually goes to infinity. Okay, let's talk about another concept here, which is about being diagonally dominant. So strictly diagonally dominant. So what is this? Well, the difference in the two Jacobi schemes, what's the two? Uh, oh, we talked about Jacobi. Oh, and then this one's another one. Okay. So this is another iteration method. So the difference in the two Jacobi schemes above, oh no, I'm kidding. The difference in the two Jacobi schemes above involves the iteration procedure being strictly diagonal dominant. We begin with the definition of strict diagonal dominance. Okay, let's talk about that. So we say we're given a matrix, right? So let's say a matrix, some matrix A is, oh, so the two schemes above. It's talking about the one that's convergent and then the other one that's divergent. Okay. I was like, where? I thought talked about a new method. Anyways, so a matrix A is strictly diagonal diagonal dominant. Uh, if for each row of that matrix, right, the sum of absolute values, okay, absolute values of the off diagonal. I was talking about the values that are not in the diagonal of the off diagonal terms is less than the absolute value of the diagonal term. So what in the world does that mean? Well, let's say we're given a matrix A, all right? So something that would be diagonal is that their K, so let's say A, K, K, A, K, K. Let's actually make it simpler. Let's do, how do I say this? We're saying that the diagonal ones are the same row and column, right? So row one, column one, and we keep going. So that's my diagonal. Okay, I'll just say I keep going. And then these are the off diagonals. So this could be like AKJ something. Same here. Some AKJ. Here I'm just saying that these are off diagonals, right? And so what I'm saying here is that the absolute value of my diagonal term, if it's diagonally dominant, then my diagonal term is greater than the sum, so I'm using a summation, of absolute values of off diagonal. So absolute values of off diagonal. That's why it's kj. What else? Yeah, that's pretty much it. And here we're just putting conditions. So j is equal to 1, or it starts at 1, but j will never be k because we're saying it's off diagonal. And we're saying it goes to n. Here we assume that A is n by n matrix or something like that. Is this a square matrix? I mean, it should be, right? No, actually, I'm not sure, to be honest. Um, yeah. So that's strict diagonal dominance. And it has the following consequences. Well, given a strictly diagonal dominant matrix A, oh, so that's the consequence. So if we have a strictly diagonal dominant A, dominant, let's say matrix A, here's the nice thing about it. So let's say we're given that, then an iterative scheme of our linear system AX equals B, it actually converges to a unique solution. I don't know, X is P, doesn't matter what it is. Let's just say it's P. So Jacobi iteration produces a sequence. So, okay, what this is saying is that if we have a strictly diagonal dominant matrix, and if we do a Jacobi iterative scheme in that, then we're guaranteed that it will converge. We will find solutions for X. So a Jacobi iteration produces a sequence P that will converge to P for any initial point. So that's the important part, actually. So if we implement a Jacobi iteration here, it will produce a sequence of p-values, unique p-values in some kth iteration, and it will converge. So it will converge to the exact value of p for any p naught, right? So if we start at any point, oh, that's what p means, point. Okay, cool. For any p naught, then we're guaranteed, if we implement this Jacobi algorithm, we're guaranteed that it will converge to p. So for the two examples considered here, this property is actually crucial, right? Okay, let's try an example because I'm giving too much theory. So for example, let's say we have a matrix A and it has these values. Or negative 1, 1, or negative 8, 1, negative 2, 1, 5. So it's a 3 by 3 matrix once more. Okay, let's look. So here we see row 1. So row 1, the absolute value of 4 is greater than the absolute value of negative 1 plus 1, which is exactly 2. That's true, right? I don't know what this means. What? Oh, something about, okay, maybe it will connect. Okay. Yeah, here, the absolute value of this. Oh, so now we're actually looking at it. in theory. The theory that we just made here. Now we're looking at it here. Okay, let's see. So this element is diagonally dominant, 4, right? And we're saying that the absolute value of this is greater than the sum of the off-diagonal values. So that's true, right? Now we look at row 2. What's the diagonally dominant or diagonal term here? The diagonal term is -8, so that's what we put in here. Is it greater than 4 plus 1? Well, yes, it is, because 4 plus 1 is 5. 8 absolute value, so 8 is greater than 5, so that's true. Now we look at row 3. Here, the diagonal term is 5, so we get the absolute value of the diagonal term, so that's 5. Is it greater than -2 plus 1? Well, yes, because that's 3. And so we say that A is strictly diagonal dominant. And so if we pick from there, if we pick any point and we use an iterative scheme, and even if we switch up these values here, we switch up the rows, right? Then in theory, we should be able to converge to a solution. Right? Yeah, and guaranteed. Okay, the textbook said it. To converge. Cool. And then there's an example of uh, a system that's not strictly diagonal dominant. And so it would diverge to infinity, or it's not guaranteed to converge. I'm not going to write the example anymore. But yeah. Jacobi. Okay, there was another method here. But I don't think, I mean, sure, we can talk about it, but yeah, there was another method. It's about, let me read it real quick, see if convergence of a scheme. So you could actually modify our Jacobi iteration, which will converge to a solution, right? Um, so yeah, we just isolate. Here, use is made of the supposedly improved value of the second equation. And what? And xk plus 1 and yk plus 1 in the third equation. Oh, in half the number of iterations. It's guaranteed with a strict diagonal dominance. Okay, so there's another, yeah, we can actually modify. Let's do that. Let's just talk about it really fast. So here it's actually just the modification of the Jacobi scheme. And we call it the Gauss, okay, Gauss-Seidel method. And it's basically a modification of the Jacobi scheme. So if you were to take our linear system that we did before, where was it? This one? Oh no, not that one. This one, right? If we take that, and if we use our Gauss-Seidel method, we'll basically get the same thing, but much faster. So let's do that. So here I don't know, I'll just say something like, we can modify our iteration using this method. Okay, I'm just gonna write it out. Okay, so xk plus 1, 7 plus yk minus zk over 4. So no modifications there. Yk plus 1 is equal to 21 plus 4x. Oh, but look at this now. Xk plus 1 plus zk. So there's the modification. And then for my zk plus 1, here we say 15 plus 2x k plus 1 minus yk plus 1 all over 5. So here's just a modification, really. But it follows the strictly diagonal dominance concept. Okay. So here we're saying that the Gauss Seidel. Okay, they call it a procedure here. Converges to a solution faster. So if we use our linear system example in half the number of iterations. So it makes it faster, right? Used by Jacobi. So our Jacobi reached like what, 19, I think? 19 iterations? I forgot. Yeah, 19. But here, if I look at my textbook, well, it reaches at 10. So yeah, about half. Yeah. 19 is close to 20. 20 divided by 2 is 10. So it reached it in 10 iterations. So like the Jacobi scheme, the Gauss-Seidel method is guaranteed to converge in the case of strict diagonal dominance. And further, the modification, the Gauss-Seidel modification, is actually only one of a large number of possible changes to the iteration scheme, which can be implemented in an effort to enhance convergence. So here we're just making convergence more efficient, right? It is actually also possible to use several previous iterations to achieve convergence. So, okay, there's this thing called Krylov space methods, which I don't think I can learn yet because it has something to do with eigenvalues based on Google, which I have yet to study. I'll definitely make a video on that when I'm done with my intro to scientific computing. But it's a way to make it faster, basically. Okay. So yeah, Krylov space methods. Something about that are often high-end iterative techniques, especially developed for rapid convergence. Included in these iteration schemes are conjugate gradient methods, so something about that, and generalized minimum residual methods, which we will discuss and implement. So yeah, that's pretty much it for iterative methods and direct methods for solving linear systems. I'm thinking of going to the last one, or I might wait it out. Uh, Let me see. Should I wait it out? Wait, let me actually just double check. Hmm, hmm. They jumped into eigenvalues here, which not my cup of tea. Okay, yeah, I might just wait it out. Yeah. Okay, that's all for direct and iterative methods. The next thing we'll be talking about is something that I'm actually interested in, which is gradient descent. So it's another algorithm used to solve the system AX equals B. And yeah, this is high performance computing. And here I'll actually be showing code in order to do that. So yeah, stay tuned for that, guys. And yeah, I'll see you here in the next one.